Hello everybody. Let me start discussion on a few more problems. Over here, this is it. It has been mentioned that the function f double dash x, this function f double dash x exists. That means function is twice differentiable in the interval a minus h to a plus h. Within this closed interval a minus h and a plus h, the function is twice differentiable. And we have to prove that this kind of expression, this kind of difference, f of a plus h minus 2 into f of a plus f of a minus h, that is equal to h square h square multiplied by f double dash at the point c, where c is a number in between these two quantities, a minus h and a plus h. You see, the whenever we applied mean value theorem, we applied those results in this kind of intervals, a comma a plus h, in this kind of closed intervals. But over here the interval is given as a minus h comma a plus h. Therefore we and the expression is also little bit different over here. So what we need to do over here, we are given that the function is this function f is differentiable two times. Then clearly this function f, uh, its previous order derivatives, that means this is second order derivative, its previous order derivative means lower order derivative means f prime, and the original function f, these two functions are differentiable, and obviously as because they are differentiable, they are continuous in the corresponding intervals, that means the interval a comma a plus h over here. Okay, and now let me draw the interval for you. Now over here we are discussing another function g, and the function g is defined in this way that f of x minus f of x minus h. Why did we define the function in this manner? Let me draw the picture for you. Over here, let us consider this kind of line. Suppose this is the point small a. This is the point a plus h, and say this is the point a minus h. Okay. Now in case of the function f, it says that the x should vary in between a minus h and a plus h. But if we consider this kind of expression, you would find that a minus h kind of expression is there. So if we try to consider x in this zone, let us suppose that this is the position of the variable x. In that case, you would see that this x minus h, this expression, this x minus h, okay, this expression would lie in this kind of zone. This may be the position of x minus h. So x minus h actually goes out of the domain of definition. However, if we now place x in this kind of position, if we place this variable x, in that case x minus h would be situated in this kind of region. Okay, and that's why over here we have taken this x belonging to the interval a comma a plus h, so that it is confirmed that x minus h lies in between a minus h and h, and we know that within this interval this function f this function f is defined, because outside the interval the function is undefined. Okay, so just we want to apply or we want to construct a function g out of this function f. Now, why did we choose this kind of difference? That is one question. Hmm. Why did we choose this kind of difference? Because you see, let me show you by writing over here the left hand side expression. The left hand side is f of a plus h. Let me write the expression of left hand side. F of a plus h minus 2 into f of a plus f of a minus h. This is the expression of left hand side, and this left hand side can be written as f of a plus h minus f of a. Let's write them within this kind of braces, minus f of a minus f of a minus h. Okay, so what we observe? We observe that this expression, this entire expression, our target is to use the mean value theorem on this entire expression. So we can now say that this expression, from this expression we can apply a mean value theorem, that this is in the form of f of b minus f of a, that should be is equal to h into f prime c. Again, this is again in the form, if you now suppose that say if we suppose that a minus h is equal to say capital A, in that case you'd find that small a is equal to capital A plus h, and therefore this expression can now be written in this way. You see, this can be written as a plus h, and this can be written in the way capital A. So hopefully, if the conditions of mean value theorem are satisfied, what are the conditions? The conditions are that the function f should be continuous in the corresponding closed interval. The under consideration over here, the interval should be a to a plus h. It is given that the function is continuous in between the interval a to a plus h. Again, over here, uh, if capital A to capital A plus h means, what is capital A? This is small a minus h is taken as capital A. So capital A plus h would be is equal to this small a. So capital A to capital A plus h would be this kind of left hand side interval. Left interval left to this small a. Therefore, hopefully, we would be able to write this expression h, this first expression. If we apply the mean value theorem, in that case, after application of mean value theorem, we can say that there exists a number, maybe suppose c1, such that this difference is equal to f h into f dash at the point c1. Got it? Minus this difference would be similarly c1. What is c1? C1 would be a number in between these two expressions a and a plus h. So we can write that say c1 may be this kind of number. Let me change the ink rather. Hopefully, rather try consider this kind of point. Hopefully, this would be the position of c1, suppose. And similarly, we can say that this difference can be written as h into f dash at the point, another point C2. C2 would be a number in between capital A and capital A plus H. So what would be C2? C2 would be a number in between this capital A. This is our capital A under consideration. This is capital A and this is capital A plus H. This is capital A plus H. So hopefully C, maybe any other number. I don't know where would be the position of C. Maybe the position of C is position of C2, not C. Maybe the position of C2 might be this kind of position. So now we can take this H common, and if we take this H common, in that case this expression would be in the form of this f dash c1 minus this f dash c2. But the problem is that over here the right hand side, this right hand side is written as f double dash c. Okay, and this h dash, this is h square. We only got a single h. Even we don't know what would be the difference in between this c1 and c2. We don't know what is the difference in between these two c1 and c2, this c1 value and this c2 value. What is the difference in between these two c1 value and c2 value? Let us call it capital H for the sake of discussion. So in that case, hopefully we would be able to write this expression in this way, that this is equal to this is our C1. So this C1 can be written as C2 plus capital H, isn't it? And again, if we apply the mean value theorem, we are given that f double dash exists. That means this function f dash is different. It is a differentiable function. That means it is a continuous function as well. So over here, this function f dash is differentiable and continuous in the closed interval c1 and c2. Okay, in this closed interval, starting from C2 up to C1, that means C2 plus H. So if we again apply the mean value theorem, we would face the problem. What is the problem? The problem is that over here, this difference would be capital H into the derivative of the function f dash, that means f double dash would ultimately appear, and certain intermediate point C would appear. But the problem is that this H, the problem is related with this H. This H is not necessarily equal to small h. Got it? So if we try to individually apply the mean value theorem on this kind of expressions, in that case we would not be able to solve the entire problem. Did you got the point? ব্যাপারটা কি বোঝা গেল কি কারণে প্রবলেমটা হচ্ছে? হুম So over here, that is the problem, and that's why in order to make up this problem, what we are doing, we are actually not decomposing or applying the we are not decomposing the expression in two different expressions. Rather, we are actually trying to apply the mean value theorem on a single expression, not individually in the first expression and individually in the second expression. So that's why what we observe is that this expression, if we now consider a function like this kind of function, say f of x minus f of x minus h, you will find that this, in that case, this expression would be let us call it, I consider this as the function g of x. In that case, this expression would be g of a. Okay, and this expression would be is equal to g of a plus h. And now, as because the function f is differentiable at the point x and x minus h both, because this is the position of x and this is the position of x minus h. Okay, let me remove this c1, then c2, and then this line is a, let me remove this, sorry, this point and maybe this point. Anyway, leave it. So in that case, this expression becomes a simple one, and now the function this x and x minus h at both of these 2 points, the function f is continuous and differentiable, and so we can say that the function g should be continuous and differentiable for x belonging to the interval a comma a plus h. If x belongs to this kind of interval, then x minus h will belong to this kind of interval. Got it? So now we can apply mean value theorem on the function g, and ultimately we will find that there exists a single number, maybe c1 or c2. I don't know what did I consider over here. I considered um, I considered in terms of theta. I considered a theta such that this difference g of a plus h minus g of a becomes is equal to h into g dash at the point a plus theta h. Got it? G dash at the point a plus theta h. Now, as because g is taken in this way, what would be g dash? G dash, this g dash, this expression, the derivative of g, that would be is equal to derivative of f dash x minus f dash at the point x minus h. In this way, so we would be able to find the derivative of the function g dash, and therefore if we replace this x by a plus theta h, in that case g dash would have this kind of expression. So that is the expression we got over here. This is the expression. So now this is this both of these two quantities a plus theta h. A plus theta h should lie in between a and a plus h, and again if you subtract h from both these two sides, in that case a plus theta h minus h, this expression would ultimately lie in between a minus h and a. So we can say that this expression a plus theta h, if this is the position of a plus theta h, then this may be the position of a plus theta h minus h. What I mean to say is that this difference, now this difference is equal to the value h. Okay, that is the main advantage of this kind of process. This difference would be is equal to h, and therefore now if we consider a plus theta h minus h as equal to capital A, in that case this a plus theta h would be is equal to a plus h, and therefore this expression now can be written in this as this difference, and so we can again apply the mean value theorem on the function f dash, because of the fact that f dash is continuous and differentiable in the interval a and a plus h. Throughout it is continuous and differentiable, therefore it is continuous and differentiable within this smaller interval. Okay, and therefore we get one more theta 1 such that this difference becomes equal to h into f double dash at the point a plus theta 1 h. And if we put the expression of a, in that case you will find that this is equal to maybe some certain number theta, maybe certain number small c. And now it remains to prove that c is a number that lies in between a minus h and a plus h. We got the expression. We got the expression of h square into f double dash c. So it remains to show that c lies in between a minus h and a plus h. So how to prove this result? Over here we have the relations that 0 less than theta and theta 1 both, and both of these two, theta and theta 1, are less than 1. Okay, so theta and theta 1 both are less than 1 and greater than 0. H is a positive number. So as because theta and theta 1, both of these two quantities lie in between 0 and 1, so if we consider the summation of theta 1 and theta 2, in that case this theta 1 plus theta 2 would be greater than 0 and less than 2. Okay, and h is a positive number, so if you multiply this total inequality by h, this less than inequality will remain be a less than inequality. Both of these two inequalities will remain be less than inequalities, and so ultimately we have this type of result, theta plus theta 1 into h minus twice h. Why we computed this kind of expression? Just looking at the expression of c, we are computing this kind of expression. Now what we need to do, we just need to add a minus h on throughout this inequality. So we shall have a minus h on the left hand side, and if we add a minus h with this twice h on the right hand side, we will have a plus h. So this is the expression, this middlemost term would be the expression of c. Therefore it is proved that c lies in between a minus h and a plus h. Got it? So in this way we are able to show that the difference, this difference is equal to h square f double dash c, and c is a number lying in between a minus h and a plus h. Okay, now is it clear to you?
Yes, sir.
স্যার তাহলে তো মানে এইচ থিটা দিয়ে করাটাই বেশি সুবিধা হবে, মানে মিন ভ্যালুর নরমালটা থেকে, থিওরেম থেকে।
মানে এইচ
মানে
এন্ড থিটা তুমি ইউজ করতে পারো, অসুবিধা কিছু নেই, যার যেটাতে কমফোর্টেবল ফিল করো। শুধু আমার বক্তব্য হচ্ছে দ্যাট ফার্স্টলি try to use, at least for this kind of problem, do not use individually, do not apply mean value theorem on this kind of individual expressions. তোমরা h theta form ইউজ করতে পারো, তোমরা অর্ডিনারি c1 c2 ইউজ করতে পারো, হোয়াট এভার ইউ ফিল কমফোর্টেবল। ক্লিয়ার? সো নাও আর কোনো কোশ্চেন আছে? নেই? তো এই কোশ্চেন, কিছু কিছু কোশ্চেন তোমাদের জন্য আমি ছেড়ে রাখছি, আমি ডিটেইলে ডিসকাশনে যাচ্ছি না। This kind of problem, let's discuss this kind of problem. Generally you had this kind of expression that x is greater than sin x, but sin x is greater than x minus 1 by x to the power of x cube, or maybe some other kind of expression would ultimately appear in subsequent terms, may appear. এই টাইপের কোশ্চেন অ্যারাইজ করতে পারে। So in order to deal this kind of questions, we actually apply mean value theorem of order 3 or 4. At least that means the Taylor's theorem. How to understand which theorem to apply, and which order term should we keep? What would be the order of Taylor's theorem? Actually, in such cases, in this kind of problems, this kind of x cube, this kind of term x cube arises in the Maclaurin's expansion of sin x for after 3 terms. Okay, so most of the times this kind of x cube would guide us to choose the value of n. This is actually a hint that we may choose n is equal to 3, so that x cube would arise. Say consider this kind of Maclaurin series expansion. This kind of Maclaurin series expansion over here, we know that f of x, the Maclaurin series says that f of x is equal to f of 0 plus x into f dash 0 plus x square by factorial of 2 into f double dash 0 plus x cube by factorial of 3 into f triple dash theta x. We are considering the Lagrange's form of remainder after 3 terms. Okay, we are considering the Lagrange's form of remainder after 3 terms. But before that, remember, we need to confirm that the Maclaudin's theorem or Taylor's theorem in Maclaudin's form is applicable at all. We need to verify whether this theorem is applicable or not. At least this is a hint that if we apply the Maclaudin's theorem up to 3 terms, then maybe we would get x cube related term. That is a hint. And in the question, it is given that x cube is there. And what would be the function? I told you that in such cases, the middlemost expression, this middlemost expression becomes the function fx. Okay. So over here, our target is to choose fx is equal to sin x in the interval. The interval is already provided in the interval 0 less than strictly less than x strictly less than pi by 2. I don't know why did I took this plus equality sign, because it is not required at all. Anyway, maybe some printing mistake is there. Even if you take x is equal to pi by 2, in that case also this result is true. Anyway, so let's continue. So in place of strict in place of this equality in the question, it would be strict inequality. This is again a question in your book uh, from maybe I don't know what is the question number. Some similar question is there in your book. Anyway, so let's continue. Hmm. So in this kind of in order to find this kind of solution, we took fx is equal to sin x. If it's given in the question that 0 less than x less than pi by 2, then you can easily take 0 less than x less than pi by 2. No harm is there. Now over here, what would be f of t? F of t is equal to sine of t. We know that this is a differentiable function. F dash t is equal to cos of t. F double dash t is equal to minus sine of t, and f triple dash t is equal to minus cos of t. So what we observe is that this function f is differentiable for all values of for all such derivative. Infinitely differentiable, basically this kind of functions. Anyway, we don't need all this. Over here, what we need to confirm that f double dash, in order to consider n is equal to 3, so f double dash should be continuous and f triple dash should exist. F double dash should be continuous in the closed interval 0 comma x, and it should exist in the interval open interval 0 comma x. F triple dash should exist in the open interval 0 comma x. So these are obvious results, but we need to state this much result. Okay, that is actually the verification process, that whether you have you know the conditions of Taylor's theorem at all. That is the proof. Generally, teachers expect this kind of verification process. So firstly, you need to verify that the f double dash is continuous and f triple dash exists in the interval 0 comma x. This much would be sufficient. This kind much statement would be sufficient as the verification process. Now, so the conditions of Taylor's theorem are satisfied for n is equal to 3. So we can say that there exists at least one number theta where 0 less than theta less than 1, such that if f of x is equal to this up to remainder up to 3 terms, and we are considering the Lagrange's form of remainder. So this is the expression. Now if you put f of x is equal to sine x, then f of 0 is equal to sine of 0, that is actually 0. Then x into f dash 0, what was f dash was equal to cos of t. F dash t was equal to cos of t. So f dash 0 means cos of 0, that is actually 1. So x into 1 would generate this x. Got it? Now again, f double dash. What is f double dash? F double dash is equal to minus sine of t. So f double dash 0 is equal to minus sine of 0. Okay, so this is the next term. Sine of 0 means actually 0. Therefore, x square related term would ultimately be vanished. No x square related term would ultimately appear over here. And afterwards, what we have, x cube by factorial of 3 is there, and f triple dash theta x. So over here, f triple dash t is equal to cos minus cos of t, and so f triple dash theta x would be is equal to minus of cos of theta x. Hmm. So we ultimately got this much result, x cube by 6 into cos of theta x. So more or less the we got a very close result, but just we need to prove the inequality. Then what to do? You see that cos of theta x for 0 less than theta less than pi by 2, for this value, and when 0 less than theta less than 1, we know that this 0 less than theta x, that is less than x, and x is less than pi by 2. Therefore we can say that this expression 0 less than theta x, and that is actually strictly less than pi by 2. Okay, and therefore in this kind of cases we know that cos of theta x is a number which always lies in between 0 and 1. Okay, so cos of theta x is a number which always lies in between 0 and 1, and therefore our target is to generate this kind of expression, the right hand side, this kind of expression. So x cube by 6 is there. So what we are doing, we this cos of theta x is there. So multiply both sides this throughout the inequality by the quantity x cube by 6. So we got this line. Hmm. Then what is x cube by 6 cos of theta x? This x cube by 6 cos of theta x would be is equal to x minus sin x, isn't it? If we consider, if you find the value of this expression, x cube by 6 cos of theta x, this much would be is equal to x minus sin x. So I am writing this expression as equal to x minus sin x, and this much is sufficient. Hmm. This much is sufficient. You see, from this first inequality, we are able to show that x, this quantity is larger and this sin x is smaller. Therefore, we are now able to show that x is greater than sin x. Okay, and again from the second inequality, we are able to show that sin x is greater than x minus x cube by 6. So the result is true for 0 less than equal this less than x less than is equal to pi by 2, and therefore it is also true in the open interval 0 comma pi by 2. Okay, so in this way, whenever we have some other higher order term like x squared, x cube, or x to the power of 4, this kind of higher order terms, whenever you have a problem related to higher order terms, you will always have to apply the Taylor's theorem here. And let's discuss few more problems. One more problem was there, really this similar kind of problem. Let me first show a check. Yeah, this one. This is again a question in your book. This is question number 27b, page number 651. You would observe that x cube related term is there. So clearly from this result, it is a hint that we will have to apply the Taylor's theorem for n is equal to 3. But we already over here, in place of two different inequalities, we have a single inequality but with this kind of modulus. Then how to prove this is exactly similar. The hint is that generally cos of 1 plus x, sorry, log of 1 plus x, this would be the function. Why do we have this kind of function? Should we consider, why should we consider this kind of function? Because you know that log of 1 plus x, you see, we already have the result that log of 1 plus x. We know that this expression is actually written in this way: x minus x square by 2 plus x cube by 3, etc. This kind of expansion, minus plus minus alternately, this kind of expansion comes in the infinite series expansion of log of 1 plus x dot 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 dot. Hmm. So actually, this kind of expansion in the subsequent classes, hopefully, I will be able to show you that this kind of expansion actually comes from the infinite Taylor's series. I did not discuss infinite Taylor series. I discussed the Taylor series only up to n number of terms. Got it? There is one more part, that is actually the extension of this Taylor's theorem for infinite number of terms. I did not ever consider this one. But this is actually a hint. You see, x minus x square by 2. Over here, this is the part x minus x square by 2 with this negative sign. In place of plus x, we have minus x. In place of minus x square by 2, we have plus x square by 2. And 1 by 3 x cube would ultimately come from this kind of term. Hmm. And that would ultimately be used, that would ultimately come from the Taylor's series expansion. Let's check how does it come. Hmm. Over here, we are choosing f of x is equal to log of 1 plus t, where 0 less than x less than is equal to t, and the domain of definition is 0 comma x. 0 less than x less than is equal to 1, because we know that this expansion is valid only when t is less than 1. Hmm. That's why we are choosing the interval 0 comma x, where x is less than or is equal to 1. Okay. Now we already know this kind of relations, f dash x, f double dash x, f triple dash x, and so on. So all these are continuous, and f triple dash exists. So we are taking n is equal to 3. We apply the Taylor's theorem with remainder after n is equal to 3 times. Hmm. And we have this type of relation. Hmm. And now what you need to know, what you need to do, just put the expression of f of 0. F of 0, f of x is equal, f of t is equal to 1 plus t. So f of 0 means 1, log of 1. Hmm. And f dash x, what was f dash x? F dash x, f dash t is this kind of expression. Hmm. So f dash 0, just put t is equal to 0, you will get 1. So f dash 0 is actually is equal to 1. So this is the x value of f dash 0, x into 1. Got it? Now what is f double dash 0? Let's check the expression. Over here, if you put t is equal to 0, in that case we will get minus 1, negative of 1, f double dash 0. So we got this result, f double dash 0 is equal to negative of 1. Now what is f triple dash? F triple dash is equal to 2 by 1 plus t whole cube. Hmm? 2 by 1 plus t whole cube. So in place of t, we are putting theta x over here. So we got this kind of expression. Hmm. So now just make a bit calculation, and finally what we are doing finally, we are just computing the last term. We are keeping the last term on the right hand side, and shift all the remaining terms to the left. Hmm. And therefore if we take the modulus, this modulus of left hand side would be is equal to the modulus of this expression, and that is actually is equal to x cube by 1 plus theta x whole cube. I removed the modulus because of the fact that this theta is positive and x is greater than 0. Therefore 1 plus theta x, that is always a positive quantity. Hmm. And therefore its cube is also a positive quantity. X is always positive, and that's why modulus of this expression, keeping modulus or removing modulus, both of them have the same values, because all the quantities under consideration are positive quantities on the right hand side. Hmm. And you see, we already have the relation that 0 less than x less than is equal to 1, and 0 less than theta less than 1. Okay, so our target is to generate this kind of expression, 1 by 1 plus theta x whole cube. Our target is to generate this kind of expression. Now how to generate it, how to construct it? What we are doing over here, we are just multiplying this relation by uh, not relation, this relation, we are multiplying this second relation by the positive number x. Okay, so this less than inequalities will remain be less than inequalities. So 0 less than theta less than 1, whenever this inequality is multiplied by x, then we would have this much: 0 less than theta x less than x, and already we have the relation that x is less than or is equal to 1. Hmm. So we ultimately have the relation that 0 less than theta x. This much is sufficient for us. Now we add 1 on left hand side and the second term. So we would have this type of relation: 1 less than 1 plus theta x. Okay, and of course this is a positive quantity. 1 plus theta x is greater than 1, so this is a positive quantity, and therefore as because it is greater than 1, so if we consider the inverse of this expression, then 1 by 1 plus theta x would be less than 1. Okay, and as because it is less than 1, therefore its cube. This is actually motivated from this kind of expression in this equation number 2. 1 by 1 plus theta x whole cube, that is also less than 1. Okay, and as because it is less than 1, so we can say that this expression, this x cube by 3, this expression, this is actually in that case less than x cube by 3. That was to be proved over here. Okay. Hmm. So that was to be proved over here. So ultimately, if we apply this result in equation number 2, ultimately we will be able to prove the result that this expression is less than x cubed by 3, and so this right hand side is less than x cubed by 3. So this expression, the modulus of this left hand side, is less than x cubed by 3, and this completes the proof. Hmm. So in this way, we have the result, and in the question, in the question, we had the inequality x is equal to 1 over here. Equality sign holds, but what considered, we considered 0 strictly less than x, less than is equal to 1. I just did not consider x is equal to 0 initially. Why? Because if x becomes is equal to 0 at the initial stage, in that case this interval would not be any interval at all. 0 comma x, this kind of interval would not be an interval at all. So initially I took x greater than 0. Hmm. But if we have to prove this result for x is equal to 0. Hmm. So what we did over here, as because we have to prove the result for x is equal to 0, we observe that if we put x is equal to 0 over here, then log of 1, that is 0. This is 0, this is 0. The left hand side would be equal to 0, and what is this? The right hand side is also equal to 0. So we can say the at x is equal to 0, the left hand side and right hand side are both equal to 0. Okay. Hmm. And therefore we can say that the equality holds at the point x is equal to 0. Okay, and that's why now if we include the point x is equal to 0 over here, we can say that this left hand side is less than x cubed by 4. Clear? So in this way we are now able to prove this result, and I'm leaving all this detailed computation or this type of examples because this kind of examples have been selected in exam, particularly for n is equal to 1 or n is equal to 2. This kind of examples were selected in exam. So I'm leaving all these discussions for you. All the detail has been written over here, and this was a question, and yes, this question as well, this question number 20. Hmm? So and similarly question number 21, this question number 21 is exactly same as the first question I discussed today in this class. Hmm? So try to use this kind of results, and this is again a similar kind of question: log of 1 plus x, I discussed this earlier. Sorry, I discussed this earlier. So this is the discussion for today. Hmm. And in the next day, I will discuss this kind of problem and mainly the infinite Taylor series. And so that's all for today. Thank you for paying attention.